Hey guys, and welcome back to another AP Physics C free response. Today we're going to be doing mechanics for 2025. This is version J, but this exam was way harder than E&M for me. I don't know why, but the multiple choice for both of those exams were pretty easy, but this free response definitely was tougher than some of the E&M questions. So question 4 is honestly pretty brutal, but let's get through it. I'm sure we'll find the right answer. And yeah, God willing, I got a 5. So let's go through this. Question 1 says two blocks, 1 and 2, slide together, or no, slide toward each other on a horizontal surface. Block 1 has mass m and slides in the positive x direction with constant speed 2v naught. Block 2 has mass 6m and slides in the negative direction with constant speed v naught, as shown in figure 1. The blocks then collide and stick together. That's important. We'll use that later because that's an inelastic collision. The collision occurs from time t equals 0 to t equals tc. After the collision, where t is greater than tc, the blocks move together with the same constant speed. So they move together with the same constant speed because they stick together. So the diagrams in figure 2 can be used to represent the momentum of blocks 1 and 2 before and after the collision. The momentum vector diagram for block 1 before the collision is shown. Draw arrows on the grids to represent the momentum vectors of block 2 before and after the collision of the two-block system before the collision and the two-block system before and after the collision. Arrows should start at the zero momentum line, and the length of arrows should be proportional to the relative magnitudes of the vectors. So represent an arrow of 0 by drawing a dot at 0. Okay, that doesn't matter. So here's what's important is that we know block 1 had mass m and velocity 2 v naught. So its momentum is 2 mv naught because p equals mv, right? That's what's important. So we know if this is 2 mv naught, then one of these bars, one of these little squares represents 1 mv naught. So now let's calculate the momentum of the other block. Well, this one is in the negative x direction, so it's negative v naught. So it's going to be 6m. We're going to make that negative v naught, and that's the momentum. So how many boxes will that take up? Logically, that will take up 6 boxes, but 6 boxes pointing towards the negative. So this is 1, 2, 3, 4, 5, 6. So right here, oops, that was on me. So it should be 6 that way. There we go. There's 6. Now, the momentum of the two-block system is P block 1 plus P block 2, which is equal to, and what would that be? It would be negative 6 mv naught plus 2 mv naught equals to negative 4 mv naught. And that is 4 boxes. 4 boxes. There we go. I don't like the arrow. For some reason, it annoyed me. Okay, there we go. Whatever. And what we also need to recognize is that the momentum before and after in the system is the same because F, the net force, is equal to dp dt. So if the net force is 0 on the system, which it is because it's frictionless, and it says they're sliding, it doesn't say the surface has friction. If the net force is 0, then the change in momentum, dp dt, with respect to time over that interval 0 to tc, is 0, right? So there's no change in momentum of the entire system. But now let's think, during the time interval, right here, it says during the time interval 0 to t to tc, a force F is exerted on block 2 by block 1 along the, oh, okay, here's the issue, along the x direction as a function of time t that is modeled by f of t is equal to f max sine a of t, where a is a positive constant and f max is the magnitude of the maximum force exerted on block 2 by block 1 during the collision. So here's what you need to recognize. On this exam, I messed up because I read on this force is exerted by block 1 on block 2, right? Or wait, no, it's exerted by block 2 on block 1. That's what I read. But this is saying it's exerted by block 1 on block 2, and that's going to be crucial when we answer this. So now it says derive an expression for F max. Express your answer in terms of these and physical constants as appropriate. Begin your derivation with a fundamental physics principle or an equation from the, okay, you get the point. I'm not going to read that every time, but it makes sense, right? So we're going to go ahead and derive what we need to derive. So, okay. Let's start. So we're given force as a function of time. So what should you immediately be thinking? Impulse, right? J equals delta P, which is equal to the integral from 0 to Tc of f of t dt. So now this is the question. What delta p, which block is having this force change its momentum? And that would be the block that's having the force exerted on it. So if block 1 is exerting this force on block 2, block 2's momentum is the momentum we should be looking at for delta p. So let's look at the delta p for block 2. Let's think. Delta p, before I compute this integral even, delta p is equal to p final 2 of block 2 minus p initial of 2. Well, I know the initial velocity of block 2 was negative 6 mv naught. That's easy enough, right? But I want to know the final velocity. So now what we're going to do is we're going to shift gears. We're going to look at the entire two-block system as a whole. We know that the initial momentum of the system was 4 mv naught, like I showed earlier, because you add the momentums together. So that's 4 mv naught. And we're going to say the momentum of the entire system has to remain unchanged by writing P final, or we could write system, sys. P final sys has to equal P initial sys. And the reason why I'm going from the two-block system versus the one-block system, I'm going to switch between the two because if I need to find the velocity of the whole block system before I find the final momentum of block 2, this is the initial momentum of the whole block system. But the final momentum must be the sum of the masses times some velocity v final. So now canceling m on both sides, I find that v final equals negative 4/7 v naught. And because v naught was in the positive direction and it's negative, that means the final velocity will be to the left, right? So now I can use that to find the final momentum of block 2. Now I can say that delta p is equal to, and block 2's momentum is the, what's it called? The mass of block 2, which would be 6m times the final velocity of block 2, because if the system moves with negative 4/7 v naught, then each of the two blocks have to move with negative 4/7 v naught, because after the collision, they stick. So times negative 4/7 v naught. And now we're going to do minus, and the initial momentum was negative. And negative negative gives me a positive, right? So now this becomes negative, negative a lot. This is so much work. Negative 24/7 mv naught plus 6 mv naught. And I'm just going to change. So we're going to change this. We're going to change it into a fraction so it's easier to work with. So 6 times 7 is, so 42 is going to go up here over 7. And what is 42 minus 24? Well, I don't care enough to do it in my head, and we get a calculator on the exam, so we're going to use the calculator. So this will spew out 18/7 mv naught. That is the final change in momentum of block 2, right? Because the change in momentum had to be positive, because the overall momentum of block 2 initially was really negative, but then it gets less negative as it collides and becomes a system with the other one. So now I can compute this integral and set that equal to this in order to find f max. So we're going to do that. So we're going to say integral from 0 to tc, 0 to tc of f max sine a of t, because that was the equation, dt equals 18/7 mv naught. And I know f max is a constant, so I can just pull that out. Oh my gosh. Sine t dt equals 18/7. 18/7. So now this integral will compute to 1/a, not sine, 1/a, it's negative 1/a, right? Yeah, negative 1/a, because this is just the rules of integration, cos at from 0 to tc. And that is going to simplify to, I'm running out of space here. So here's what I'm going to do, you guys. I'm going to take all, no, I'm going to select all and just scale it down a little bit. if you guys don't mind, and I'm going to zoom in a little bit. F max, and now I'm going to apply the negative, so I just switch my bounds. And then I'm going to change the integration bounds. So I'm going to apply that negative. It's going to become 1 over a cos. And when I say apply the negative, I mean I'm just going to change the integration bounds and drop the negative, right? So now this becomes, I'm going to evaluate this again, F max. Oh, I could just divide by a here and not have to do it to each term. It's going to be cosine of 0 minus cosine of a TC, right? And that becomes F max A cosine 0 is 1 minus cos ATC. And now that is equal to, like I said earlier, 18/7 MV naught. And now we'll just do some simple algebra to find that F max is equal to, 1 second, F max is equal to this whole, whatever it is, contraption, solution, but hey, if it works, it works. That's what you needed to get. That's the right answer. Probably. Let's check. Did I make any mistake? Okay, sorry about that, guys. So yeah, this is the correct final answer here. 7, 1 minus cos ATC, and there, hopefully you guys understood the work to get there. Now I'm going to delete all of this. So this is still for question 1, but we are going to look at question 1, part B. Consider a new scenario where block 1 initially slides in the positive x direction with a new constant speed v1, and block 2 again initially slides in the negative x direction with constant speed v0. The blocks collide and stick together. In the new scenario, the two-block system has constant speed v0 after the collision. Derive an expression for v1 in terms of v0. Okay, so now we're going to basically just do this by using conservation of momentum. So they're still sticking after the end. So what we're going to say, I shouldn't zoom in so much, is P, please stop moving. We're going to say P final is equal to P initial of the system. So what was the initial velocity? Well, what was the initial momentum? The initial momentum will be 2mv1 because block 1 initially slides with 2mv1, and that's going to be minus 6m v0, right? Because this is sliding to the left in the negative x direction with v0 again. And that has to equal to, now they stick together. So now the two-block system has a constant speed of v0 after the collision. So now the two-block system, after they stick, that means their masses add. So their masses add up to, oh, wait, why did I put 2mv1? Oh, my bad, you guys. It's just mv1. That's on me. It is just mv1. mv1 minus 6mv0. Now I add their masses, I get 7mv0. And I put v0 because it says they slide with speed v0 after the collision. So now we're just going to solve this. mv1 equals 13mv0. Cancel the m's. v1 equals 13v0. But you might be asking, well, hey, how did you know that this final momentum was in the positive direction? What if it's in the negative direction? They just said it has a constant speed v0. They didn't say it has a constant velocity positive v0, and you're absolutely right to think that. In fact, I thought that on the exam, so I tried it. What if it was negative, right? They might give you points for showing this. I highly doubt it. But what if it had negative velocity at the end? Let's try it. mv1 equals, now I'll add 6mv0 to the other side. I'll get negative mv0, and I'll get v1 equals negative v0. And you might be thinking, well, hey, now I have two answers. Which one do I pick? You don't. Read this question again. It says, block 1 initially slides in the positive x direction with a new constant speed v1. This is negative, clearly negative, because V naught is a positive constant, a positive V. And if it's saying this equation is saying V1 is equal to negative V naught, that's telling me block one is moving to the left. But the problem clearly states it's moving to the right. Therefore, your actual answer is 13 V naught. That is the only possible answer for this question. Hopefully that cleared up some confusion, but now let's move on to question 2. Okay, this question I was super happy to see because we did a Smart Illinois problem on this when in the simple harmonic motion unit, and I was like, oh my gosh, there's no way they just gave me this question. I was so happy. So let's read it. In scenario 1, a system is composed of two springs, A and B, and a block of mass m is at rest on a horizontal surface. Friction between the block and the surface is negligible. Each spring is attached to a fixed wall and the block, as shown in figure 1. Spring A has spring constant K, and spring B has spring constant 2K. Each spring is at its relaxed length when the block is at position x equals 0, as shown. The block is moved to x equals x1 and held at rest, as shown in figure 2. An energy bar chart can be used to represent the elastic potential energy UA of spring A, the elastic potential energy UB of spring B, and the kinetic energy K block of the block. On the energy bar chart, draw shaded bars to represent the kinetic energy, to represent the energy of the system for when the block is at x equals x1. Any energy equal to 0 should be represented by a distinct line on the 0 energy line. The height of the shaded bars should be proportional to the relative values of each of the energies. So let's think. When it's at x equals x1, what does this thing literally tell me? It says the block is moved to x equals x1 and held at rest. What's the kinetic energy? 0. It is held at rest. How can there be any kinetic energy? Bang, that's one of them done. Now we have to think, well, which one UA or UB will have elastic spring potential energy, and how do I represent them with the relative magnitudes? I don't know the length of x1. I just know it's x1. You don't have to know. It told us here, spring B had 2K, but this one just had K. So they're being compressed or stretched the same distance, and you know that spring potential energy is 1/2 kx squared. But now, if they're being stretched the same distance, this is the same for the two, but they have different k's. Well, UA, let's say I'll just plug in x1 for UA. It's 1/2 k x1 squared, right? Now for UB, well, I'm compressing it that same distance, but it's 2k x1 squared. So therefore, UB has to be double UA. So now I can just arbitrarily, let's say I pick UA to be like this high. UB has to be that high. Does that make sense? Hopefully it does. And don't use the bottom. There's negative energy does not exist unless you're working with gravitation, electrical potential energy, and some other energies. But for usually you won't have negative energy, but it can totally pop up on E&M or gravitation. So there we go. That's the bar chart for that. Now B, the block is released from x equals x1 and begins to oscillate. Derive an expression for the speed v of the block as the block passes through x equals 1/2 x1. Express your answers in terms of m, k, x1, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or equation from the reference information. There's two ways to do this problem. One, you can recognize that the equivalent spring constants of springs connected like this in this specific situation, when normally you'll think, hey, well, now I have springs connected like this, like in series. I do this 1/k thing, right? In this situation, it's the exact opposite. Because there's a block in between the two, you can just add the spring constants, and that's the equivalent spring constant. And that's what I'm going to do because I don't feel like doing the other one. The other one's too long. But actually, you know what? I'll do both because I want you guys to understand both situations. Because if you understand both, then you'll be fine on the exam. So let's do both. Now we'll declare KEQ equals 3K. Bam. Okay. Now I know what was it asking me? I forgot. Derive an expression for the speed v of the block as the block passes through x equals x1. There's no friction, so energy final has to equal energy initial. Like whenever you're asked for a speed, you should usually think conservation of energy. And if you can't do conservation of energy, do the simple harmonic motion equations. So E final equals E initial. Well, what's E initial? It's US has to equal, well, K plus US. Well, I'll say US initial has to equal US final plus K final. Okay, great. So what's US initial? Well, it's 1/2 3K and that was at x1 squared, which is equal to 1/2. The mass of the block had mass m, so 1/2 m, and I'll call that v final squared. And then I know it was at 1/2 x squared, so I'll put 1/2 x1 squared here. And what does that give me? That gives me 1/2. Actually, that gives me 3/2 k x1 squared, and I'll just subtract this from in order to get mv final like by itself, because you know separation of variables and all that good stuff. So 1/2 squared times 1/2 is going to give me, it's going to be 3/8 x1 or k x1 squared, right, is equal to 1/2 mv final. Well, what if I multiply everything by 2? Now I get 3kx1 squared minus 3 over 4k x1 squared equals mv final. What if I multiply everything by 4? This is a lot of what ifs sometimes, you know, because instead of working with fractions, it's sometimes just easier to multiply things out. So I multiply it by 4. And now here I will get, what's 12 minus 3? Probably a number that I don't feel, oh, it's 9. kx1, wow, I feel stupid. And now that's equal to 4mv final squared. Now I'll just simplify, divide by m, take the square root in order to get phi final. And when I simplify this, this will give me 3 over 2 x1 square root k over m. This is your final answer, right? That should be what you get. But now let's do the other route. If you didn't know that the equivalent spring constant is that, that's okay. We're still going to use conservation of energy. We're going to say that the initial spring potential energy, we're just going to do the individual spring potential energies. I'm not going to do the whole thing. I'm telling you right now, I'm not going to do the whole thing. So I'll just show you. The individual spring potential energies, the initial will be this. And can you see how if I add these two, this becomes 3 over 2 kx1 squared? And what did I have over here? It's the same thing. And it's going to be the same thing on the other side, because once I add them, it'll just become this. So I'm not going to run through that, but you could have done the individual spring potential energies for A and B, or you could have combined their equivalent spring constants and done it that way. So now I'm going to delete all of this and move on to the next question. In scenario 1, the block oscillates with period t, and the position x of the block in scenario 1 as a function of time is shown in figure 4. Great. So this is the position as a function of time. In scenario 2, my voice cracks so bad. In scenario 2, the block spring system is placed on a new surface. There is friction between the block and the new surface. The block is again moved to the same position, x equals x1, and is released from rest. The block completes multiple oscillations with the same period in scenario 1 before coming to rest. On the axes shown in figure 5, sketch a graph of the kinetic energy K as a block as a function of time t, shown in scenario 2. This is what they want you to recognize. So this is part C. This is what they want to see. This is what they want to see. AP Physics. No, I'm fine. So this is what they want you to know. They want you to recognize that the kinetic energy is 1/2 mv final squared. So will this graph ever be negative? No, because velocity, even if velocity is negative, it will square itself and then it'll become positive. You can't have negative mass. 1/2 is a positive by definition, right? So there is no negative part of this graph. Now we need to recognize what does, and I know that here, look at this graph. Is this a sine graph or is this a cosine graph? Let's think. Well, it's a sine graph because, sorry, it's a cosine graph because look, it starts with a y-intercept. Sine graphs don't start with a y-intercept unless you phase shift them, but that's not what we're doing in simple harmonic motion. Like they teach it to you, but it usually doesn't show up. So I know that the velocity has to be a sine. And if I square sine, it'll look something like this. That looks horrible. If you could, please go on Desmos and look at what sine squared looks like. It will give you the correct general idea for what you need to do for this problem. So I'll just tell you right now, sine looks like this. Oops. It has to max out twice. twice before completing the full period, but it will max kind of like this. It'll dampen. That's what they want to see. That's the thing. Mine looks horrible. Do not do it the way I do it. Yours should dampen a little bit better. Here, I'll show you. It should complete two peaks like this. I'm going to plot mine out like this. It should complete two peaks in one period, right? It should complete like that. And it should continuously just dampen because of the friction. Energy is being lost. What they want to see is dampening. Now, let me tell you what I did. I did this. Sorry. I did this. like mine dampened, but it dampened per period. Like I thought, you see how these are equal peaks? That is not what you're supposed to do. Do not do that. Do it the way I did it earlier, right? Here, I'll show you. Whatever. Is this erasing up here? Okay. But yeah, moral of the story, make it dampen like that. Right? Because a simple harmonic oscillator will always dampen. All right, I'm not going to write out problem D because my handwriting's really bad. I will just explain it. Here we go. In scenario 3, the block is replaced with a new block of larger mass. The coefficient of kinetic friction between the new block and the surface in scenario 3 is the same as the coefficient of kinetic friction between the original block and the surface in scenario 2. The new block is moved to position x equals x1 and released from rest, so the same position. The kinetic energy of the new block is now plotted as a function of time. Describe how one feature of the graph of k as a function of time t in scenario 3 would differ from the graph you drew in figure 5 for scenario 2. So here's what we have to think. Did I leave? Oh, did I not draw it? Whatever. I guess I have to leave this. Okay. So if you have larger mass, we know kinetic energy is 1/2 mv final squared. But I also know that the force of friction is mu mg. So if I have a greater kinetic energy, sorry, I don't have a greater initial kinetic energy because I don't have a greater initial energy in general because the initial energy is 1/2 kx squared. K didn't change and the initial x didn't change. So the kinetic energy has to be the same initially. So it'll start, the change in kinetic energy will go like, I guess it won't reach as high a peak. Let me show you what I mean. This is what 2 would look like. The initial spring elastic energy will be the same, but this is what the other one would do. Why did it not change? Whatever. So this is what the other one would do. It would kind of dampen like that. It would dampen faster, you know? So the reason why it would dampen faster is because the force of friction is greater. Don't say faster. What you should say is it will dampen more per period. What I said is per each period, the graph of K will dampen more due to a greater force of friction as work equals the change in kinetic energy. Since work is proportional to mu mg d and m increased, therefore delta K must also increase. I'm not going to write that out. But delta K must also increase. And if delta K is increasing, then it has to dampen more per period, right? Does that make sense? I hope that made sense. But that's basically what I said. Yeah. But what you could also say is that the graph will stretch like in period because t equals 2 pi square root m over k. And if you have greater t, or if you have greater m, then the period will also be greater. This will stretch that way. That's also something you could say. I just went a different route. You might have thought one, you might have thought the other. Go for either. You know what I'm saying? Get that point. So let's move on to question 3. A box is connected here. This one I will write because I fear that this is one of the harder questions. A box is connected to one end of a rigid rod. Both the box and the rod have negligible mass. The other end of the rod is connected to a pivot. The box is open on one side and the block is placed inside the box. The center of mass of the block is displaced a vertical distance h as shown in figure 1. The box system is then released from rest and swings downward. There's negligible friction about the pivot. When the system is at the lowest point of its swing, the rod collides with a rigid stopper, as shown in Figure 2. The box comes to rest, and the block is launched horizontally out of the box. The block moves across a horizontal surface towards a motion sensor that measures the speed of the box. All frictional forces are negligible. So now here is the next question. Students are asked to experimentally determine the acceleration due to gravity, g, using a linear graph. To determine g, the students are permitted to use measurements from only a meter stick and a motion sensor. Great, that's all we need. Describe an experimental procedure using the described setup that would allow students to determine an experimental value of g using a linear graph. Include any steps necessary to reduce experimental uncertainty. So this is what we need to do. Like I did in E&M, I'm going to list step by step, and we're going to think, how can I get gravity from this thingy? How can I get, well, let's think. Do you have to go through all the complicated physics? When it stops, right? When that stops and there's a collision between the two, that this will impulse there and that will push back on that. No, you don't need to think about it because they're not giving you all of these complicated things. They're just saying vertical distance h, and it flies out with the speed v. So what should you be thinking? Conservation of energy. E final equals E initial. You can also think V equals square root 2 GH, because that is what this will simplify to, and I will prove that later. But what you should intuitively be thinking is that what I want to measure is the height. They gave me a meter stick, so 1. So measure height h and record it. Ensure you measure twice before recording for less error. Done. Next question. Or sorry, not next question. What am I saying? So the next step, release the box and measure V as it's sliding. And it said it's sliding, right? It moves. It moves across the surface. My handwriting's horrible. Okay, 3. Repeat steps 1 and 2. Displace. For 1, I should say displace delta y, a delta y, h, and hold the box there. So when I say displace a delta y h, my handwriting is so bad. I mean displace the box a vertical displacement y, which is equal to h. So repeat steps 1 to 2, 5 to 10 times, increasing h each time, and measuring each time. So there, we got experimental uncertainty, we got the procedure, and we got the values that we need to record. So now I'm going to leave that there for a little. You can pause here if you want, but I'm going to delete this so I can move on to the next problem. So B, describe how the data collected could be graphed and how that graph could be used to analyze, or whatever it is, determine the value of G. I should amp this up. Yeah, that's better. So here's what we're going to do. What we're going to do is we're going to use E final. Oh my gosh, what did I? Oh, I fat fingered that. We're going to do E final is equal to E initial. We're going to say UG has to equal K final. Then we're going to say MGH has to equal 1/2 MV squared. Cancel this. And we're going to say we're going to say V equals 2GH. V equals square root 2GH. But now I'm going to separate the 2G and the square root H. And now I'm going to draw an arrow this way to indicate that I want to plot V as a function of square root h. Slope equals square root 2g. Therefore, slope squared divided by 2 equals gravity. Done. And there, if you were wondering how I got there, if slope is equal to 2g, because look, this looks like, this is the linearization part. If this looks like, this is my y, this is my m, and this is my x, m is slope, and if slope is equal to square root 2g, I can square it to get slope squared equals 2g. Slope squared divided by 2 equals g. So there we go. That's that question. Now here's C. The experiment is repeated, but the horizontal surface on which the block slides is replaced with the new surface as shown in figure 3. The coefficient of kinetic friction between the block and the new surface is mu. The block box system is pulled aside so that the center of mass of the block is displaced of various vertical distances h and then released from rest. For each vertical distance, students measure the position x equals x max at which the block comes to rest. The students' measurements of x or of h and x max are shown in table 1. Indicate two quantities, either measured quantities from table 1 or additional calculated quantities that could be graphed to produce a straight line or that could be used to determine mu. So now, here's what we're going to do. Like I did on E&M, I'm going to skip to part D because they're asking me to indicate two quantities. When they ask you to do that, they're asking you linearize and tell us what you're going to linearize so we can see, so we can read your graph, right? Right? So when they ask you indicate two quantities, they're basically telling you linearize. But part D gives you points. Part D, let me get this hair off my screen. Part D gives you points for linearizing. So why do it on a scratch sheet of paper when you're going to be asked to do it for points anyway? So we're just going to skip to part D and start the linearization. So we know that work is the change in energy. So what force did work on this system to change its energy? So now we're going to think, well, what's included in our system? Well, we have the block, but we want to keep gravity in the system because we don't want to think about the work done by gravity on the way down. No, that's so much work. Literally so much work. Well, I don't want to think about that. So I'm going to include gravity in my system, and we're going to say that the only work that was done on that block to dissipate its energy is the force of friction, or the work done by the force of friction. So we're going to say work equals change in, not kinetic, change in mechanical energy, which is equal to E final minus E initial. Okay, well, what is E final? Well, it's not moving and its gravitational potential is 0 because this is what I'm calling my height 0, right? And then I'll call that 0. So now work is equal to negative E initial. Well, what was E initial? If I stretch it a vertical distance h, well, my initial energy was UG, so now it's negative UG. Well, I know work is a dot product of the force that did work and the distance that it did work over, and that has to equal negative mgh, which is negative mu g. But now, what is the force of friction? Well, sometimes when it's on an incline, it might be different, so we're just going to work it out here. So the sum of the forces on the y of this block are force normal minus force gravity. And if you need to, you can draw out the free body diagram. It looks kind of like this, Fn, and then Fg, all that. You see they're balanced. And even while it's sliding, it's not accelerating in the y, so I know that the sum of forces is 0. Therefore, the normal force is equal to the gravitational force, which is mg. But I also know that the frictional force is equal to mu k times, sorry, the kinetic frictional force. Mu k times Fn. So therefore, the frictional force is equal to mu k mg. So now I'm going to sub that in on the left side of this equation. Right? Now the distance that it moves, let's visualize the block while it's here. It has a displacement vector that is positive in that direction. I'm going to zoom in so you guys can see. So it has a displacement vector that's like this way. But what way is the force of friction acting on it? Well, that would be the opposite way. I'll do that one in green. That is the opposite way. So now I'll put these vectors tail to tail and I'll think, well, this is FF and this is D. And what's the theta between the two? Oh, it looks like a line, and that means theta is 180. So I know a dot product is the values of the two vectors times cosine of the angle between the two. Cosine of 180 turns into -1, and I know that's equal to negative mgh. So now guess what? Negatives cancel, m and g cancel on both sides, and I get this equation. Oh wait, negative mu k mg x max. So if you're wondering why I just put that x max there, the reason that I'm multiplying x max by that entire thing, because work is force times distance. And the displacement that work is being done over, the distance work is being done over, is x max, right? Because the displacement is final minus initial. Well, its final position is x max. Its initial is 0. Therefore, the displacement is, well, guess what? X max. So therefore, I can just go back and put x max as the displacement, and I get this equation. H equals mu k x max. This is looking a lot like a different equation. Y equals mx. It's literally the same equation. H corresponds to a displacement in y. Mu is, oops, mu has m literally, oops, mu has m literally in the name, and x max is x. So now it's spoon fed to us in this situation. So now you can identify mu k as your slope and say slope is equal to mu k, which is equal to delta h over delta, what was the other one? X max. So now I know what I'm going to plot. I identified my dependent variable, which is horizontal axis, or my independent variable, and I identified my dependent variable, which is y, right, which is h. So now I know what I'm going to put in this section. I'm going to put on the vertical axis, I want h, which is measured in meters. You always got to tell them the units. And I want x max, which is measured also in meters. And another way you could check this answer is to understand that when I divide something by its own unit, because h is in meters and x is in meters, meters divided by meters, well, the units cancel, and now I get a number with no units. Mu is a number with no units. So the fact that mu is equal to slope, that's correct, because we know that our slope will have no units, and mu has no units, therefore, bam, they're the same, done. So that's just another way to verify it. So now here we're going to do the actual part that came before part D. So on the grid provided, create a graph of the quantities indicated in part CI. Use table 2 blah, blah, blah. Basically, they're just telling you graph. So this is what you need to do. It says clearly label your axes. Great, I'm going to do that. Did I? Okay. HM, done. X max, done. Oh, meters. You need to figure out. So now you need to put m for both of them. You need to put the units for both of them. So now what I'm gonna think is, okay, wait, what was I gonna say? Oh yeah. So now what you need to think is, I have this table of the values. How am I gonna scale these axes? Well, I see h is going from 0.3 to 0.9, so why don't I just go from 0 and I'll go up by, like, say 0.2 so we can get to 0.9. That gives me 0.6 here, 0.8. Not 0 point, it'll give me 1, and then here I'll get 1.2, bam. So now I have all the range of values that I need for h, but now what about the values I need for x? Let's think about it. What if I go from, like, 0.5s? You could totally do that. You could go, here's 0.5, here's 1, here's 1.5, here's 2, here's 2.5. Now, albeit, here's 3. You might only end up using, like, this section of that graph, but that really doesn't matter. You know, they don't care as long as you use half, so you'll probably get the point. It's not probably, it's very likely you'll get the point. So now I have my range, and this bottom axis is really easy to figure out, because what are these increments? Well, they go up by 0.1 until they get to 0.5. So that's really easy. So now let's think. Let's plot each of our points and find a slope. So 0.3 is the 0.3 is the height, and 0.76 is the x max. Well, let's find 0.76. Here's 0.5, here's 0.6, here's 0.7, here's 0.8. 0.76 is somewhere in the middle, but a little bit past that. So it's probably going to be like there. And I know 0.3, more like there. It doesn't really matter. And I know 0.3 is in between 4 and 2. So it's in between 0.4 and 0.2, so I'll just plot that point right about there. And done. The next point is 1.1. Well, 1.1 is right here. That's pretty easy. And the y. So I know it's 1.1, and what's the y? Well, the y is 0.45. Well, that's pretty easy. If here was 0.5, because it's in the middle, 0.5 is in the middle of the middle, so it's like right there. So 1.1 is right here, 0. That's the next point. Now this is starting to look pretty linear, which is a good sign. The next x comma, or the next point is 1.4, which corresponds to 0.6. Oh, great, I have a point for 0.6. This is even easier than I imagined. So there we go. And now it's actually starting to look linear, which makes me happy. So now I know 1.9 is the next one. So right here, there's 1.9. 0.75. Ooh, 0.75 is in the middle of the middle. So we'll do that same thing again. So now here's 1.9. The middle of the middle is there. Uh-oh. Oh, wait, no. It's in the middle of the middle because there's 0.75. So now here's 1.9. There's 0.75. Done. Now we can move on to the next point. Now it's 2.3. So 2.1, 2.2, 2.3. There we go. And what is the 0.9? Great. So 0.9 is in between 1 and 0.8. So 2.3, 0.9. There. And now this is looking pretty linear. So I'll just pull out this ruler. Plot this nice line that I have. And great. Nice linearized line. I'm actually gonna change the slope of that a little bit. Why is Apple messing with me today? Oh, that's fine. Here we go. Because I want it to pass through 0, 0. Actually, no, I shouldn't want it to pass because then I'll mess it up. So there's my line. And that's fine. We can leave it like that. So now we have to pull points off of this line in order to find the slope. So that's easy. Let's just pick easy intersections. Bang, there's an intersection. That is 1 comma, what's the y? 0.4. Great. Let's pull another point. Is there anything here? Let's see, maybe I can extend it and find a point. Okay, let's just use this one. It's 3 comma, and what's that, y? It's like almost 1.2, but not yet 1.2. What is this increment? It's 0.2 divided by 5. Let's see what Google has to say about that. And if you're asking me if I can't do that division, no, I can't, and I don't feel like doing it, so guess what? I won't. So it's 1.2 minus 0.04, and this is like 1.16. So now we'll do change in y is 1.16 minus, what was the other one? 0.4 divided by, and it's 3 minus 1, which gives us a slope of, let's check Desmos, gives us a slope of 1.16 minus 0.4 divided by 2, 0.38. And there is mu. So you guys see, that wasn't honestly that bad. I just really don't like linearizing. It used to be my worst actually, but now it's my best question. And I hope that this helped you guys even a little bit with linearizing, because I like to talk through my thought process, and I feel like that might help you guys know how to approach these problems. So yeah, let's move on to the next question, and the last question of the night. Question 4. This was the hardest question. A uniform disk and ring, each of mass m and radius r, roll without slipping along a horizontal surface as shown in figure 1. The outer edges of the disk and ring are made of the same material. The center of mass of the disk and the center of mass of the ring initially move with the same constant speed v. The disk and the ring then smoothly transition to a ramp at an inclined inclined at an angle theta above the horizontal. Both the disk and the ring continue to roll without slipping as they move up the ramp, as shown in figure 2. The ring travels a greater distance along the ramp than the disk does before each momentarily comes to rest. While the disk and the ring are rolling on the ramp without slipping, the magnitudes of the static frictional force exerted on the ring or on the disk and ring are Fd and Fr respectively. Indicate whether Fd is less than, greater than, or equal to Fr by writing one of the following. Justify your answer using qualitative reasoning beyond referencing equations. This is what we need to think. This question is honestly really difficult because we can't use equations and we have to use qualitative reasoning. I don't like using qualitative reasoning. I'm an equation guy, and you might not be that, or you might be. Either way, we're in the same boat, we're answering the same question. So here's what you need to do for this question. We need to think. The static frictional force, we know that the friction as a function of the opposing force looks like this. So this is mu s, right? But then mu k will be constant because as I have a block and I push on it more and more and more, at some point friction will stop opposing, like friction will reach its maximum and then it'll become less than its maximum. That's just how physics how physics works, right? You can push on like a table and at some point it will give. So that's the thing here. The static frictional force is not necessarily proportional to the mass. It's proportional to the force that's being applied to it. So let's think. And I'm gonna leave space because here I'll write FD is whatever, whatever. So I'll just use my reasoning. I'm going to say that since I'm gonna use Newton's second law, here's what I'm gonna use. Since some forces, no, we're gonna say this. Since and it tells us, the ring travels a greater distance along the ramp than the disk before each momentarily comes to rest. Since the ring travels a greater distance than the disk, its A translational must be less, as the two have the same V naught, and delta x equals V naught t plus 1/2 AT squared. We'll say minus. And now I know they said not to reference equations. I don't care. This is the only way you can do this, and I'm gonna say that. So therefore, the sum forces on the ring must be less, as F is proportional to MA. And since Newton's second law dictates that and I'm going to pick my direction of acceleration this way. Actually, I'm going to pick the initial velocity to be the positive. So here's V naught. Here's V naught, and here's V naught, and the acceleration is going to be down the ramp. Dictates that negative friction, because friction is actually going to act down the ramp. No, gravity is going to act down the ramp, and friction is going to act up the ramp, is equal to negative mg sine plus F, which is equal to ma. Therefore, since both, or you know what, they don't like this. They like this. We'll not say mg sine theta. We'll say fgx. Since both have the same fgx, negative fgx, less a means more f. Therefore, and now I'm going to come back and complete it, the force of friction on the ring has to be greater than the force of friction on the disk. And let's hope that's the right answer and I didn't leave you all astray, because it should be. Let's see. So the hoop does have a higher static force of friction. So what I'm looking at my key, I just said, since the component of the gravitational force is the same for both of them, and static friction, the reason why static friction pulls up the ramp is if I visualize they're both rotating, and if they're going to move to the right, then they have to rotate clockwise. If you rotate clockwise and you're making contact with an object, friction is going to oppose the motion. The motion will be clockwise, so the friction will be counterclockwise. Counterclockwise would be up the ramp. So now if you have less acceleration, right? And g sine theta, like the force gravity x is negative, if you have less of this, oh wait, oops, negative ma. So if you have less acceleration, then that means fgx, negative fgx plus f has to be, well, greater, right? Like that means this sum has to be less, meaning that this friction has to be more. Because if you have less friction, well, guess what? A is going to be greater. Negative A will be greater, right? So therefore, more F. So what you need to reference is basically that fact that they gave you. The ring travels a greater distance. The ring travels a greater distance. Therefore, it has less acceleration. Therefore, by Newton's second law, it has to have more friction because more friction means less sum forces, which means less negative acceleration. Bam, done. And that was a lengthy explanation, and I apologize for that, but I hope it made some sense because that was the question um, that really confused me, and I was really sad about getting that one wrong because, like, the reason I got that one wrong because I skipped part B, which we're about to do, and I missed the negative. And you saw I just missed it there. I wrote it in right here. I missed the negative on negative MA. And for that reason, I derived everything and I got the right final answer. Just I missed one negative. So my answer was wrong. And then my reasoning was wrong because I based part A off of part B. So always pay direction or pay respect to the direction of acceleration, you guys. It might cost you some points, but I hope you guys don't make the same mistake I did. So just keep practicing. And I believe in all of you. You will all do fine on the exam. So now let's do part B. So a cylinder has mass m, radius r, and rotational inertia I about its central axis. The cylinder rolls without slipping up a ramp that is inclined an angle theta above the horizontal. Derive an expression for the magnitude of the static frictional force exerted on the cylinder by the ramp. Express your answer in terms of these things and physical constants as appropriate. So what we're going to just do, we're going to start Newton's second law. We're going to write it right this time, of course. So we're going to say that the initial velocity, if it's rotating up the ramp, I'm just gonna call I'm gonna call like here, I'm gonna draw this. Oh wait, no, I have the drawing over here. I'm gonna call this way my positive, this way my negative. So my negative is negative fgx, plus we're gonna call that f is equal to negative ma, because it's accelerating down. Because if it's gonna stop at some point, then it has to be accelerating down, right? So now what we're gonna do is we're just gonna solve. We're gonna move fgx to the other side, minus ma. So f has to equal mg sine theta minus ma. So now what I'm going to do is I'm going to use torque to get what a is because I'm allowed to use g sine theta m and everything else, but I'm not allowed to use a. So I'm going to use some tau equals I angular acceleration. And I'm going to define my direction of positive acceleration to be, or positive angular acceleration to be that way, just so I don't have any confusion. Because I only have one torque, so I'm going to define the positive to be in the direction of that torque. So therefore, I angular acceleration is equal to radius times force sine 90 degrees, because on this, the friction is applied like that. Here's the radius vector. Oh, guess what? This is 90 degrees. Bam, 90 degrees between the two. So sine 90 simplifies to 1. So now I get I, and alpha is really A divided by R, is equal to RF. Is equal to RF, right? So therefore, I can simplify this equation. I get R squared F divided by I equals A. So now I'll sub that in back here. I'll get F equals mg sine theta minus m r squared f divided by I. Well, now I have two f's, so now I have to separate these two by adding that back to the other side. Wow, funny. But it's fine. So now I have this equation, right? Because I just basically added that back to the other side of the equation. I'm going to select on, decrease this, and now I'm going to factor out f, and I get 1 plus mr squared divided by I is equal to mg sine theta. So now I get the force of friction is equal to mg sine theta divided by 1 plus mr squared divided by I. Sorry for my handwriting. I'll do a little bit better there. And that's your final answer there. So yeah, always pay respect to the direction of the acceleration. And you can also reason out why the ring would have less or greater static force of friction, because as I goes to infinity, right? If I have greater and greater I, this number will get closer and closer to this number will get closer and closer to 0. This number will get closer and closer to 1, and that will make the force of friction less as compared to, well, actually, that will make the force of friction more, right? Because if I have a number here, I'm increasing the denominator, which means I'm decreasing the overall like number. But if I'm decreasing the denominator by kind of eliminating this term, then I'm increasing the number overall. So more moment of inertia means a more static force of friction. So there we go. And now for part C, this is what I'm going to do. I'm going to say, I know this question because I'm on low battery. I'm going to say, in a different scenario, the centers of mass of the original disk and ring have the same initial speed v as they did in the original scenario. The ramp is then replaced by a new ramp on which the disk and the ring initially slip as they roll up the ramp. Indicate whether the magnitude of the kinetic frictional force exerted on the disk by the new ramp is greater than, less than, or equal to the magnitude of the kinetic frictional force exerted on the ring while both are slipping. This is what you need to remember. For kinetic frictional force, this is what the force of friction as a function of the force applied kind of looks like. So as you apply greater and greater force, there's a threshold, like it reaches its max. But after that, when it's slipping and you have kinetic friction, because here's mu s and here's mu k. For every force applied, no matter what, if you're slipping and there's kinetic friction, mu k will be the same. Mu k will be the same because mu k times mg equals FFK, the force of friction kinetic. But the force of friction of mu adjusts according to the force that's applied to it. While mu k doesn't care the force that's being applied to it, it just cares that it's moving. So does that make sense? So therefore, the two forces are equal, right? So yeah, that was pretty much it. I really hope that you guys learned something from this video. And I hope that your exams go well. I know it's summer, but like in a year you'll be taking the AP Physics C exam if you haven't already. And it can be a daunting exam, but my reminder to you all is that just to breathe during the exam, make sure you don't make any reading errors, and it's okay to not do the best on the exam, because at the end of the day, what you learn in the class is more valuable than what you get on the exam. And there's always college placement exams. So if you find yourself in a spot where you're struggling to understand this, because this was a really difficult question, and I like had to struggle with like, wow, I messed that up. That was really like I was really happy about this question because I like had asked it in class. But what you guys should really be focusing on is your development as a physician, like as a physics person. So this test, just a reminder, this test doesn't define you. So I hope you guys will do really well in your exams and your coming exams, and you enjoy your summers. So yeah, that's it for me.